Hey, I'm glad you're back. I have to say, I have been absolutely loving these new running shoes I bought. They're so comfortable. My feet feel like they're running on clouds. Seriously, I've been raving about them to everyone. My friends, my neighbors, random joggers on the trail, even my doctor when I went in for a checkup yesterday. Oh, don't worry, it was nothing serious. It started with the usual stuff, but then I found out my doctor had an extra surprise in store for me. Decked out in my new running shoes, my doctor had me run on a treadmill to test how my heart was working. After the test, my doctor showed me the graph of my heart's activity. And guess what? It looked just like some of the functions we discussed in our last lesson. I can't remember the graph exactly, but this is kind of what it looked like. Just pages and pages of this. It was so long, so maybe we just extract a portion of it. The start of the test, and forget the rest. Let's zoom in on that, and let's throw this function on a coordinate plane. We have time in milliseconds here on the x-axis, and voltage. So my heart's electrical activity is in millivolts on the y-axis. Now, do you see where my graph crosses the y-axis here? Well, that's a specific point called the y-intercept. It's a point where the function intersects the y-axis. A y-intercept always has to be on the y-axis. That's why it's a y-intercept. So what do you think is always going to be true about the coordinates of a point that's on the y-axis? Yeah, if it's on the y-axis, then its x-coordinate has to be 0. And the y-coordinate will just be some number, let's call it y, on the y-axis. What are the coordinates of the y-intercept in this function? It's 0, 0.4. So what does that mean in terms of my heart's electrical activity? This means that at 0 milliseconds into the test, my heart's voltage was at 0.4 millivolts. Great. Now let's think. If the y-intercept is the point at which the graph crosses the y-axis, what do you think the x-intercept might be? Exactly. The x-intercept is a point where the function intersects or crosses the horizontal x-axis. And if the y-intercept takes the form of 0, y, what do you think the coordinates of the x-intercept will be? Exactly, x, 0. Can you find an x-intercept on this function? We actually have 2 points here where the function crosses the x-axis. They're here at approximately 130, 0 and 200, 0. This means that around 130 milliseconds into the test, my heart's electrical voltage reached 0. And then that happened again at 200 milliseconds. Now, how many y-intercepts and x-intercepts do you think a function can have? Well, let's rewind to a few lessons ago. How can you quickly tell if the graph of a relation is a function or not? By doing a vertical line test. Imagine if I had more than one y-intercept, like this relationship, if we did a vertical line test along the y-axis, then it would fail and, well, it wouldn't be a function. So functions cannot have more than one y-intercept. As for x-intercepts, you can have as many or as few as necessary depending on the scenario. Like with sketches of a heart's electrical activity, a patient's heart might reach a voltage of 0 4 times, maybe 2 times, maybe never. All possible scenarios and all functions that will pass the vertical line test. Now that we've figured out intercepts, using the same graph we've been working with, let's explore another important feature of functions. the intervals where the function increases or decreases. You may be asking yourself, what does it mean for a function to increase or decrease? Well, a function is considered increasing over an interval if the function is moving upwards on the graph as we read it from left to right. On the other hand, a function is considered decreasing over an interval if the function is moving downwards on the graph as we read it from left to right. Pause the video and see if you can determine in which sections the graph is increasing and in which sections the graph is decreasing. Let's scan or read the graph from left to right. I'll highlight green for increasing and red for decreasing. Imagine yourself trying to travel along this line from left to right. Would you be going up a hill or down one? Up. So it's increasing. How about here? Would you be going up a hill or down one? Down. So it's decreasing. And here, up a hill or down? Up. So it's increasing. All right, so it looks like my function starts increasing for an interval, then decreasing, and then it begins increasing again. But I can't always just point or highlight a graph to show where it's increasing or decreasing. I have to be able to describe it mathematically as well. Let's take this first section where the graph is increasing as it moves from left to right across our x-axis. How do you think we could describe this increasing section of the graph in both interval notation and inequality notation? Pause the video here and give it a go. We can describe this interval where our function is increasing as all the x values from 0 to 80 milliseconds. But, should 0 and 80 be included in my interval or no? Well, let's think. This increasing section creates a hill. So imagine that you're climbing up that hill. When you're standing right at the bottom or all the way at the top of the hill, are you moving up in those moments? No, you're not going up or down in those moments, so we won't include 0 or 80 in the increasing interval. Pause the video here and see if you can describe the remaining decreasing and increasing intervals now. We can describe this decreasing interval on the graph as all the x values from 80 to 140 milliseconds. Just like last time, we won't include 80 or 140 as decreasing values. If we picture this interval like climbing down a hill, right before you start climbing down and right when you get to the bottom, you're not actually going down at those points, so we can't include them in our decreasing interval. How about this last section that's increasing? We could describe this increasing interval as all of the x values from 140 to 200. Again, not including 140 or 200 because you aren't actually climbing a hill when you're at the base or when you reach the tippy top. As you can see, writing in inequality and interval notation allows us to precisely describe the different intervals over which the function was increasing or decreasing. And that is the final attribute that we're going to use in our work on analyzing the graphs of functions. So let's put everything we've learned in this lesson together into 2 example problems. This example asks us to analyze the graph of the function below to list the intercepts as well as the intervals over which the function is increasing or decreasing, written in interval notation. This graph doesn't have any written scale on the graph, so we just assume it goes by ones. Pause the video here to list these attributes of the graph, and then come back and see how you did. Let's start with the y-intercept. This function crosses the vertical y-axis at the point 0, -3. How about the x-intercept? Well, this function only crosses the horizontal x-axis one time, and that's at the point 1, 0. As for the intervals over which the function is increasing, that's here, here, and here. We can write those 3 intervals as 0, 2, 6, 8, and 8, 10. But we can view those last two increasing intervals as one big increasing interval. Since the line never stops increasing, it just gets steeper once it gets to 8. So I'll combine these and list the interval 6, 10. As for the intervals over which the function is decreasing, well, nowhere. There is no section of this function that is decreasing. But what's happening here? Is the function increasing or decreasing over this interval? Neither. The function is not increasing or decreasing here. It's remaining constant at a y value of 3. All right, let's keep practicing with one more example problem. Similar to the previous example problem, here we're going to analyze the graph of the function below to list the intercepts, as well as the intervals over which the function is increasing or decreasing. This time written in inequality notation. Pause the video here and list these attributes of the graph on your own now. The y-intercept of this function is at the point 0, 5. As for the x-intercepts, there are none. There is never a point where the function crosses the horizontal x-axis. Now, before we get into the increasing and decreasing intervals, I want you to take another closer look at this function. Do you see how this function has an arrow at this end and no arrow at this end? What do you think that signifies? This means that the function has an endpoint here and goes on forever to positive infinity here. When a line has an arrow like this, you can assume it is going to continue with the same exact behavior forever. So we can assume this graph will continue increasing to positive infinity and never change its direction. If you didn't notice these details of the function before and want to edit your answers, go ahead and pause the video to do that now. Given this information from the function, we could say that the function is increasing from 0 to positive infinity, while the function is decreasing from -10 to 0. Nice work. Just as the visual representation of my heart's electrical activity can help doctors understand the story of my heart during the stress test, the graph of any function gives us so much information and details about a variety of scenarios. Today, we strengthen our analysis of graphs to include several more key attributes, like a graph's y-intercept, x-intercepts, as well as increasing and decreasing intervals. Isn't it amazing how much of a story can be told through a simple graph? Awesome work today. Once you're done watching this video and you've completed your guided notes, you'll find a few more opportunities to practice analyzing functions in the additional practice found in your PDF. And once you're ready, go ahead and complete the online practice game. Whew, my new shoes need a break. I think we're gonna take some time to rest up, but I will see you next time.